Welcome back to physics. Now it's time for us to work on a new way of delineating the relationship between energy and force. So we can kind of conceptually understand that there must be some sort of relationship between force applied and the change in energy of an object, because we know circumstances in which we apply a force and change the energy. For example, if you threw something upwards, right? If you took an object and you threw it up, when you're throwing it up, right, it starts out with no kinetic energy, and then you throw it, and in the act of throwing, you're giving it kinetic energy. And you're doing that via the mechanism of applying a force. So there has to be some sort of relationship there. Similarly, when you catch something, right, it initially had kinetic energy as it was falling because it had a speed, but when I caught it, it had no speed anymore. So somehow I'm applying a force and decreasing the kinetic energy of the object. Now we could also do like weightlifting, right? If you take an object and you apply a force to lift it up, then you must be somehow adding energy to it, right? Because you apply a force to get like potential energy up, and then you bring it back down, potential energy decreases, right? And that's all done via the mechanism of applying a force. So the question is, what's the relationship, formally speaking, or physically speaking, between force and energy? We've already implied it's between force and changes in energy, but let's go through it in an actual formal physics way. This is called work, right? And what we're going to do first is derive work from scratch. We're going to derive a formulation for work, right? Because we know, and we actually did in some previous questions, that you can calculate the energy change from the details of the force applied. So let's do that, and then we'll come to a formula for how this energy change works. So we have a constant force, F, is applied to a mass, m. The object's speed changes from u to v. The change occurs over a distance, s. Now we want to calculate some sort of relationship between F and the change in potential, or sorry, in this case, the change in kinetic energy. So the change in kinetic energy is going to be equal to 1/2 mv squared minus 1/2 mu squared. Right, so far so good. And that is going to be equal to, let's say, it's equal to 1/2 mv squared minus 1/2 mu squared. I've just put the gaps in. All right, and that's going to come in handy a little later, but I'll rub out those gaps so you don't think there's a thing there. What have I done? I've rubbed stuff out. Okay, cool. Let's also bring in a Newton's kinematic formula. V squared equals u squared plus 2as. Interesting? Maybe. Now, when we push our object, right, there was a force exerted on it, and let's assume that that was the only force exerted on the object for the time being. If that force were to be divided by the mass of the object, we'd get that F over m is equal to a. And so let's substitute that in our equation. V squared is equal to u squared plus 2 times F over m times s. So far, so good. Now we're going to take our Newton's kinematic equation and we're going to subtract the u squared from everything. So we're going to take v squared minus u squared is equal to 2 times F over m times s. So far, so good. We'll do some rubbing out. So we've got this formula. Now what we're going to do is we want to somehow make it look like this because we want to represent the change in kinetic energy. So I'm going to multiply, and by multiply I mean divide both sides by 2. So we get 1/2 v squared minus 1/2 u squared is equal to F over m times s. Then multiply every side by m. 1/2 mv squared minus 1/2 mu squared is equal to F times s. And you see something interesting here. By using Newton's second law, F equals ma, and substituting into our formula, v squared equals u squared plus 2as, and that alone, I've realized that this quantity, which is the change in kinetic energy, is simply equal to the force applied to our object multiplied by the distance over which it goes. How interesting. Force times distance is change in energy, in this case. Let's try another case. Let's try, we have a constant force applied to an object of mass m, right? Now we're going to assume that this constant force is what is required to balance the object, right? And the object's height increases a total of h meters. So let's say our object, our force, is going to be equal to mg, right? This force balances the mass of the object, and then the object's height increases a total of h meters. So, the total energy change, right, delta U, is equal to mg, technically h, right? H is the amount that it rises, so we could write delta H if we want to. So we can. But if we assume that the force is simply equal to the force opposing gravity, some sort of person force to lift this up, then delta U is equal to force times h. Once again, we arrive via some simple mathematics at the idea that the force multiplied by the distance over which it acts, the distance over which the object moves, is equal to the change in energy of that object. Well, that's what work is. The work done by a force on an object is the force applied to that object. It must be constant, multiplied by the distance that object travels while that force is being applied. Now, it does not need to be true that the object moves because of the force, okay? The force simply needs to be applied in the same axis as the direction of travel. For example, if one were to push an object, if the force and the displacement are in the same direction, the energy increases. If the force and the displacement are in opposite directions, the energy decreases. In this case, it means that if W is greater than 0, energy increases. And if W is less than 0, energy decreases. Keeping in mind that F and S both have a direction, right? They're going to have, in our case, either be positive or negative, right? We would define some direction as positive, and we would say, okay, well, the force is in the positive direction, and the displacement is in the positive direction. One thing I want to emphasize is that S is only the distance traveled while the force is being applied. So if you're pushing an object, the instant you stop pushing, you stop counting the distance. Okay, it's only while you are pushing that it counts. So for example, if I were to throw this object up, right, when I throw it, you'll notice there's a brief instant where I'm pushing, I'm accelerating the object, and my hand's still attached to it, right? Like I throw, and there's that instant where I'm still lifting it up, right? As soon as my hands leave, we're not talking about work done anymore, right? Because I'm not applying a force to this object anymore once it's kind of free flying. You may ask, well, Tom, isn't gravity still applying a force to that object? Absolutely, and we will get into that very, very soon in the next video. So that's the definition of work. Force times distance, keeping in mind that if force and distance are in the same direction, it's positive, and if force and distance are in the opposite direction, it's negative. Because W, work done, is a scalar, right, with the SI unit of joules, it can only be positive or negative. It's essentially saying, is energy added, positive, or is energy subtracted, negative, right? Like if you catch an object, right, if I were to throw this and then catch it, in the catching, it's going down, but I'm exerting a force up. So we catch it, and it kind of is me exerting a force up while it travels down. Those two are opposite directions, and so the work done is negative. The energy is subtracted. So let's do some simple calculations of work done. Remember this one? We had a box being pushed, and we had to calculate the final kinetic energy of the box. And how we did this last time, right, is we did the force, then we calculated the acceleration, then we calculated the final velocity, then we calculated the kinetic energy, and then we calculated the change in kinetic energy, because that velocity allowed us to find the final kinetic energy. we can do it way easier. We can do it way better. So what we're going to do is we're going to realize that work done, which is equal to the change in energy, is equal to force times distance. That's going to be equal to 200 newtons times 3 meters. That's it. There was a 200 Newton force. It was applied over 3 meters. The change in energy is 600 joules. Right? And we did so much work in the previous question, the previous video. Actually, it's technically the first video on kinetic energy. Look at that towards the end. Did this calculation. This is so much quicker, so much easier. Right? That's the change in energy. The work done is equal to the change in energy. We can also do it for gravitational systems. We have our object here, mass 5 kilograms, dropped from a cliff of height 230 meters. What's the work done by gravity? In this case, you don't really gain much in simplification, but we'll do it anyway. Right? What is the work done by gravity over the course of the journey? Well, work done is equal to the change in energy, which is equal to the force times the distance, which is equal to mg times s, which is 5 times, now what we could do is say negative 9.8 times negative 230, right? If we're assuming up is positive, then it goes down, the force is down, those two are in the same direction, so our work done should end up being positive. So 5 times 9.8 times 230 yields 11270 joules. And do you remember that was one of the answers we had for our previous video? So that's work. It's a useful concept. It's just going to tie into some other concepts we've done, right? Like it's just another way of doing stuff that we've already actually done, right? And we derived it from formulas that we already had. It's nothing new. It's just a quick thing. Okay, it's a useful formalism. Now, there's the entire possibility that there's more than one work at a time, right? Like you could be pushing an object one way and there could be friction acting the other way. And in that case, both of them do work on the object that you're pushing, right? You add energy to the object that you're pushing, and the friction is taking that energy away, right? If you are ever asked for the total change in energy of the object, you add up all the works, right? You add up all the work you're doing, you add up all the work friction is doing. Obviously, there'd be an opposite sign because friction would apply a force in the opposite direction to motion, so F and S would be in opposite directions, whereas when you're pushing it, presumably, F and S are in the same direction. But the question might ask you, what is the work done by something, right? So for example, when I throw this object or when I lift this object, right? You can ask for the work done by me, but you can also ask for the work done by gravity. And those will be different answers, right? Because the work done by gravity means considering only gravity, calculate work done. Or work done by friction would be just use friction, right? Don't calculate the work done for other cases. And this is very important because what we're going to do is we're going to see this kind of law of conservation of mechanical energy. What it's going to say is that kinetic energy and potential energy when combined should always not change, should remain constant. And then you'll be like, oh, well, then how can there be work done, right? And it'll be like, well, technically, there can be work done by different things, right? There can be work done by gravity, work done by air resistance, that sort of stuff. Let's try a couple more examples. A person pushes a block a total of 3 meters, applying a force of 25 newtons. What is the total work done on the block by the person, right? Got to get into the correct vernacular here. It's kind of like indexes again. So the work done is equal to the force applied multiplied by the distance. In this case, we're assuming we put the forces in the same direction as the distance. So that's 25 times 3, which is 75 joules. Okay. But a corollary. That block has friction resisting it. Okay, so if we have our object here, our block here, someone is pushing it to the right, we'll call that F push, and we've got friction, F friction to the left. And the block's velocity is constant. So what's the work done by friction on the block? Well, if the block's velocity is constant, then the change in kinetic energy is 0, right? And that means the total work done has to be equal to 0. Which means the work done by this force, the push force, and the work done by the frictional force have to be equal and opposite. And so that means the work done by friction has to be negative 75 joules in order for it to cancel out this positive 75 joules. Another way you can think about it is if the velocity equals 0, then according to Newton's first law, the forces must sum, if the change in velocity equals 0, so the velocity is constant, still true, that the net force must be 0 according to Newton's first law, meaning these two forces have to be the same value, meaning that the frictional force is 25 newtons as well. And that means the work done by friction is going to be 25 times minus 3. Technically, minus 25 times 3, they're in opposite directions, right? So that's going to be 75 newtons, joules. Similar sort of thing. But you'll notice that we've only done one dimension so far. So what are we going to do for 2 dimensions? Actually, not too much, right? Actually, it doesn't matter. This is the best part about work. Because it's a scalar, directions aren't supposed to factor in. Meaning that if we have a force in some direction that is not along the axis of S, right? So it's not directly with or directly against S, just take the component of that force that is in that direction. We only take, for example, F cos theta. So in this case, the work done would be Fs cos theta, right? And that's actually the proper definition of work. That work done equals Fs cos theta, where theta is the angle between F and S. So F and S are actually both vectors. And what this is called a dot product, which, don't worry about it, right? It's a thing. But F and S are both vectors, and therefore they must have an angle between them. And this angle is theta. And this gives us some delightful stuff. For example, if theta equals 180, then F and S are in opposite directions, right? That's having an F this way. And cos of 180 is 0. This jiggling is annoying me. Right? Cos of 180 is 0, so we can ignore it. Slay. Exciting. If theta equals 90, well, cos of 90 is 0. Sorry, cos of minus 180 is minus 1. That's what I meant to say. Right? So, saying my statement again. If theta equals 180, that's cosine being completely opposite to the direction. So the direction of force and the direction of displacement are completely opposite. Work should be negative, and cos of 180 is negative 1. Easy breezy. If theta equals 90, so work and displacement are orthogonal to one another, sorry, force and displacement are orthogonal to one another, no work is done by that force. It might be the case that work is done by other forces, but no work is done by the force that is at right angles to the displacement. So that's the real work equation, okay? And it actually already has that kind of plus and minusness in it with the cosine. So let's do an example calculation, and then that's it for work. A person is pulling on a block with a force of 30 newtons, 30 degrees above the horizontal. So it's like this, 30 newtons, 30 degrees. And it's, Tom didn't specify the mass of the block, so the mass of the block is now 10 kilograms. Lol. Nice work, Tom. Does the mass of the block matter? No. Doesn't matter. But I put it in anyway, even though I shouldn't have put it in, right? Because I don't practice, right, ahead of time. I just do. Like, I just take these slides and I just go. And I was like, oh, Tom, you need the mass. And then 10 seconds later, no, you don't need the mass, but whatever. The block moves horizontally a total of 10 meters, so we have an S of 10 meters. What's the work done by the person pulling? Well, let's assume that S is to the right and the force is to the right. We have to kind of assume they're in a similar direction. They have the same X component. Work done, force times distance times cosine of the angle between force and distance. In this case, 30 times 10 times cosine of 30. And that's it. which is 260 joules, thereabouts. And that's work. It's pretty easy, it's pretty fun. In the next video, we're going to be talking about force conservation or energy conservation, which is going to round out our kind of energy formulation. So thank you so much for watching this video. I hope I'll see you in the next one. And here's a celebratory dab.